Mhm. I mean, should we just get started?
Yeah.
All right, sick. Well, welcome to the day one of mechanalysis. Yeah, you call it mechanal, I'm beating you up. But for real, thanks for taking this experiment with y'all. We're super excited, and we think it's going to be a lot of fun. So today is going to be more of an overview day and like a little bit of review. So like to be a little frank, if you've taken mech solids already, the first like few classes are going to be mostly review. So just get out of it what you want to get out of it. But other than that, let's get started. Bottom line up first, we're going to start every lecture with just kind of like what the agenda is. So we're going to do a quick icebreaker, introduce everyone, introduce the team, go over like what inspired this class, why we want to do it, and why we're teaching it, introduce y'all to CAs, and then go over some like logistic stuff of like how we're going to be using platforms in this class, and then brief review of like free body diagrams and some like mechanics of solids. So just as a quick icebreaker, we want you to introduce yourself and your pronouns, and then say your name, your favorite engineering tool, starting with over there.
I'm Ellie. I use they them pronouns.
Good one.
My name is Rajiv. I use he, him pronouns and Cameron.
Good one.
I'm Gabe. I use he, them. I would say the electric
My name is Emily.
I'm Rohan. And I'll go with
Oh. Exotic.
I'm Gino. He, him pronouns. I'm gonna go with surface plate.
My name is Rowan, he, him, and I like the powder coater.
I'm Tara. She, her. I like caliper.
Nice. Precise.
I'm Avery. He, him. I would say the handheld plasma printer.
Also fun.
I'm Rohan. He, him. I'm gonna go with school.
Yeah, that's right.
And I like digital torque wrenches.
Also great.
I'm Maya. I use any pronouns. My favorite engineering tool is Julia. I use she, her pronouns. Her favorite tool for writing is actually Google. So much.
There we go. There we go.
I'm Anusha. She, they.
Nice.
I'm Laurel. She, her. And I entirely forgot this. Oh, zip ties.
Also great.
As I'm Colin, he, him, like a steel rule. I'm Nathan, he, him. Hard to choose a favorite, but kind of like in sandpaper right now.
That's oh god, manual labor. Carlos, he, him. I'd say the oxyacetylene torch. Yeah, cut through some thick steel with that guy. We have a few intro slides, and first, a moment of silence, please.
So currently Katie is, she's like the fourth member of this team, but right now she's on a plane heading to Italy for a study abroad program this semester for her final semester at Olin. So send her lots of good food thoughts. She's from Ann Arbor originally. She's a big themed entertainment person. She interned at Universal Creative for 2 summers and is hoping to go back full time. She loves bubble tea. Sarah Slush is a favorite. Former project manager of DBF, former shop assistant. Big fan of UX design. Worked at Onshape and did UX design for them. And yeah, currently in Italy.
And because she's that much of a real one, she's still helping like with the class even while like she's not even going to be here. So big thank you to Katie. We love her. My name's Carlos. You'll probably know me. I'm from San Antonio. I got 2 dogs, Zuki and Fauci in the bottom left. I'm the former PM of Baja. I have a very astute love of Whataburger. And I am a current shop assistant, and I am your average wind energy enthusiast.
Colin, from Cedar Valley, California. I have a single dog named Wally, whose tongue constantly sticks out.
Oh, wait, really?
Former mech lead of Formula. I guess I do a lot of digital photography, a very casual milling machine enjoyer. And then I have an unhealthy addiction to banana milk, and I've been deemed a closeted Disney adult by my class.
Yeah.
I'm Nathan. I'm originally from Columbia, Missouri, out in the middle of nowhere. Two dogs, Pilo and Ollie. Pilo's the one with the next to the pillow, and Ollie's up there in the top corner. I've been formerly on leadership for both rocketry and design and fly. I love all things that fly. I've done a couple of aerospace internships, and I really enjoy food, model airplanes, taking pictures.
Yay. All right, so how we're going to kick off class is that we're going to start with a very quick, like maybe 5-minute activity. So with your people at your table, I want you to consider if you were assigned like a mechanical design project, or you had to do some sort of analysis for a job, and you had like no idea what to do. So like there's 2 examples up there, but you like have no idea and you're in out of your depth and you've never experienced this thing before. What resources would you go to and how would you start figuring that out? What we want you to do is like share that with people at your table, just like talk about it for a few minutes. And then after you're done with that, please go to this Yell key on your phones, your laptops, and like we would love for you to compile those lists and do a very quick share out, just because we want people to like, the base of this class is we want to help build your toolbox of when you haven't explicitly been taught something, how you go about and analyze it so you can actually get it done.
And also, all these lecture slides are on the J document.
Oh, yes. Yes. Yeah. Give a big thank you to Colin for figuring out Canvas.
This Yell key will expire, but the link that in the slides will still work in the future if you ever want to go back and reference this document. Get a more accessible place later on.
Yeah, we might do some QC on it. I don't know. Guess I should. Oh yeah, can Kai hear us?
I hope so. Are you there, Kai?
We're muted. Oh wait, no, Nathan's not. Okay.
Sorry, I can hear you guys just fine. Thank you.
Sorry, say that one more time.
I can hear you guys. Thank you.
Oh, perfect.
Right now, no. Like we're if you just want to hang out and do some work, like we have one side where we're just going to introduce like CAs, and then just kind of like I know office hours are still being worked out right now, but like so like not even 10 minutes. We can also just skip to it right now.
Either way, I'll hang out for minutes and I'm gonna go eat.
Okay.
Okay.
I'm not so hungry. I need it much.
Here,
I'll hang
how
out.
about at the end of this activity, we'll just like introduce the dates and it'll be a slide. Do you have a? No, you'll be. Don't worry about it. Thank you.
Thank you, Matt.
Yeah, I got it.
That is your.
Or works formulas.
Say SolidWorks forms.
Works formulas.
I haven't heard of that.
That sounds good as one.
Yeah.
Not as good.
If on the document, please include hyperlinks. If you're not like, don't just say the name of the resource. If you could actually like put a link to it, that'd be awesome.
Bad according to who?
Yeah.
I call my dad.
Yeah.
That is a valid thing.
I mean,
You should
I
put
want
it on
your
the
dad.
way, yeah.
So.
But talking to people is a really
Share the
super
digit.
valid way to
Yeah.
learn stuff. So yeah.
Mhm.
Take it to number 1.
Oh, someone already has it. Thank God. Good.
That's a great sheet.
Yeah. Yeah. You should well, side question, and please be honest, raise your hand if you didn't even remotely look at the like the review materials. Okay, that's not bad. That's not bad. There is a resource. Yeah. there is a like beginner, and you guys should have access to edit that. At the bottom of that page, there is a review like database of like really great channels and like websites and textbooks that we have found useful during our own career. That's fair. Yeah, that's entirely valid.
Chris Lee.
That's also valid.
Yeah,
That's entirely valid.
Chris Lee. How do I get names?
I know, might have misplaced that one. I don't know.
Brian Story, mechanical mixed solids lectures.
I guess.
Not bad, but
Yeah.
maybe not always intuitive.
Mm. Brian Story, not intuitive.
Yeah, whoa. No one buy a Toyota vehicle.
The water analogy is so useful.
I liked it. I don't know. I all right, I don't know whose timer that is, but I feel like that's a good timer for us too.
Yeah. Anybody else have anything else you want to add?
Oh, nice. Cool. Does anyone feel particularly inspired to share theirs, or are they seeing something that they've never seen before or super like it? Very nice.
Super enthusiastic.
Cool. Is this actually this? Can we pull this up?
Actually, I should check the mirror real quick.
Yeah. Awesome. All right, I'm seeing a lot of resources that I'm pretty familiar with actually, but I'm not familiar with MMPDS.
Yeah.
Mm.
Very nice.
Yeah.
What is so it's a
So like a bunch of companies who did material research got together and just made a big sheet, and it has like everything you need, but also like thermal knockdowns.
oh, that's sick.
You have to pay so much money to access it.
I'm
sure. I'm
It's also
sure.
like IHS, one of those crazy.
I tried to get it.
Yeah, that's awesome. Oh, really? That's hilarious. But you should, yeah. Stack Exchange is great. I love that as well. Not, I've used Ames Webs like once. I have used Brian Story's lectures, regrettably. I had to watch those videos to help hold Mech Solid office hours, and yay. So that's great. Jeff Hansen, godsend. Love that man to death. Also represent Texas Tech, so guns up. And Olin shop training is awesome. All of this is here. We'll sift through these and maybe add them to either the course website or something like that. But what's really great is that like what we want you to get out of this class is we want you to be more familiar with resources that are out there, because it's really hard to like know what you don't know. And there's just so many resources out there, most of them free or easily accessible or easily piratable. But like what we want to do is, because a lot of times like at Olin or even elsewhere, there's a kind of like expectation that like I haven't been exposed to this before, like I must not have any way to actually do it. And we want to like dispel that notion, because you guys are all capable engineers, and we totally believe that like you guys can basically tackle any job when you have no idea how to do it. So jumping back to the slides. Nope. There you go. There we go. The next thing we want to do is that, share with the list, partner key. The next thing we want to do is just give a quick kind of like history lesson of how we got in this position and like what we aim to and complete with this course. So number one, Jeff leaves Olin. And so because Jeff leaves Olin, we think that Mech Solids is not going to happen and be dead for this semester. And we are, as Olin seniors who are deeply concerned about the Olin community, we are worried no one will get rolling ruler content. So we go to the mechanical engineering professors and we're like, hey, like we're a bunch of like young studs. Like we really want to teach Mech Solids. Like we got a lot from this class. All of us were enrolled in the Emily's Mech Solids our sophomore year. And honestly, I feel each of us could say that like our biggest regret about it is that we didn't get it earlier. Getting introduced to Mech Solids is like, in my opinion, the first time I felt like I was doing real mechanical engineering work. That's not entirely true, but like it was a really great jumping off point and we super loved it. So we went to the academic resource board and we're like, we want to teach Mech Solids. They said no. Mech Solids is a core curriculum class. And so they were like, you guys, like, we love the enthusiasm, but we can't let you teach a core class. From other Olin history, data science was student-led course. And so like they had to test out of it. If you have a student-led course, and it's a core curriculum class to graduate, you have to, the students have to take the course, they get credit for it, but then they have to test out for whoever the teaching advisor or the content advisor is for whoever teaches the class. And there was a huge thing with that where someone actually didn't pass the test and it was like a big thing and they like didn't know how they were going to graduate and they had to like hustle in the last minute. So they don't want to invite that again. But they did say like, you guys really should teach a Mech Solids 2.0 class. Like whoever said that earlier, that is kind of like what this class is. Like in the ideal, like mechanical design, like not including transport and thermo and all that stuff, like the pipeline as it should work is that you get introduced to Mech Solids and then in MechDes, you learn more content and like you start doing actual complex like analysis projects and like building and designing your own machines. Like it's mechanical design. In actuality, there's actually kind of a big gap between there. So full disclosure, I did not take MechDes. I had an opportunity to take a class elsewhere, a transfer class, and that fulfilled my MechDes requirement. But everyone I've talked to has always said like they wish they had more stuff going into MechDes, and that like it feels like there's a gap in between those things. That gap can be filled with project teams, it can be filled with internships and co-ops, or just like hanging out with professors, going to the machine shop all the time. Like that gap can be filled. But we really wanted to have their like it be baked into the class. And so you get exposed to resources that you might not know existed elsewhere. Like we don't think you being a competent engineer, a mechanical engineer should be dependent on you like spending hours working on a project team. Like you should be exposed to this in class, even if you don't get all of that. So if you go to the course website on Canvas, there's a whole syllabus out there. Please read through it. Colin did a ton of great job on it. But basically what this class is that it's supposed to bridge where you leave from Mech Solids and where you're supposed to be for MechDes. So like in our ideal world, when you guys get to MechDes, we want you to like be able to completely and confidently design and analyze your structures so you can defend it. Like my biggest piece of advice I always give to Olin first years or candidates or even on my tours is that like because Olin is so like not like intrinsically motivated, like at the end of every project, you should ask yourself, can I defend this project in a technical interview? Like, can I talk about it and not just say, oh, it works? Like, can I explain why it works? So that's what we want to do with this. This class is going to be a blend of kind of Mech Solids stuff. Machine Elements is another class that you'll take or that you would take in a more traditional like school environment. And we're also going to bring in some special topics. So like I said, for the first few weeks, 2 or 3 weeks, we're going to be doing some revisiting some Mech Solids and speedrunning that. So we're going to like really kick in free body diagrams into y'all because you're going to need to do that for MechDes. And I feel like I've been talking a lot. Do you guys want to say anything about the free body diagram experience in MechDes?
I'm taking MechDes.
Oh, that's right.
So I took MechDes last year, and when we first arrived, during the first like chunk of the class, we like started rolling into stuff and started like taking on projects and it was moving quickly and everything is looking okay. And then a couple of weeks in, Dave kind of realized that, it's all very complicated, right? But long story short, that especially, in part because of COVID, in part because of like the curriculum and the state of that at Olin, there was a kind of this big dip in just basic free body diagram skills. That's not anybody's fault. It's just, it happened. And so we had to spend the first 2 or 3 weeks reviewing just how to like trace forces back through a structure, things like that. So if you already can knock that out ahead before you run into MechDes, you'll be able to just like the stuff you'll be able to do in MechDes will just be much better because you will be able to knock out all that remove all that extra time that you use to review.
Yeah, and we also know there's a handful of you who've never taken Mech Solids or are currently enrolled in Mech Solids, and so like we don't want to just leave you behind in the dust. We're going to like spend a little bit of time going through that. If you have trouble, look at our resources, come to office hours. It should be fine. But for Mech Solids, we're doing free body diagrams, reviewing stress transformations, and revisiting a few things about beam bending, and also adding a few items to your beam bending toolkit, like singularity functions or superposition, stuff that you don't really get introduced to in Mech Solids. For machine elements, this is what the bulk of the class is going to be. This is going to be your mechanical design, machine design, Things we're going to talk about failure theories, when things fail and why, beyond just like, oh, it's reached its yielding point, like more complex stuff than just a 1D tension test. We're going to discuss fatigue, why things fail way before they should in the yield test, where things rubbing together, shaft loading. We're going to talk about bearing life design. We're going to talk about gear design, how to analyze a planetary gear set, and we're going to talk about bolt design. Because like it's actually way more complicated than just tight, like get it till it's good and tight. Some special topics that we're also super excited about. We want to throw in a quick FEA overview. So we're obviously can't teach you everything you need to know about FEA, but we think it's a very important thing to know and have more knowledge behind, ooh, pretty colors. We want to talk about ethics as well. Katie has a really cool thing lined up for where we're working at Universal Studios. She's talking to her former boss about like the ethics of like when shit fails, people die. And so like it's beyond just like I need to build this, make it cheap, tight. You need to make it safe. And it's beyond just like this Hyatt bridge collapsing. Like we really want to like it's not the focal point of the class, but it's an aspect we wanted to bring in. And we're also reaching out to alumni speakers and see if they want to talk and do anything like that. So like, it should be a really fun class that we're super looking forward to. Some acknowledgements. I personally, the entire team wants to thank Dr. Ben Black. He is a part-time professor at UT Austin, and he taught the transfer class I took from UT Austin. That class was called Machine Elements, and a lot of this curriculum has been adapted based off that. So he sent his materials and was super excited about it. He's a great guy, and UT Austin, hook 'em horns.
So for the majority of this course, we're teaching through Shigley's, if you're not aware. It's also going to be in the reserve shelves in the library. We're also going to have a digital copy soon on Canvas. And then you should be familiar with Gear if you worked on Mech Solids. That's the course textbook for that one. And then we're also just going to be pulling from random textbooks that we feel are relevant when the times arise. For the general structure, we are meeting, of course, like Monday, Thursday, 8:30 to 10:10. We're going to have one short homework a week. Like Daniel noted, there is a bunch of homeworks on there right now, but they are far lower in kind of workload for y'all. We've kind of set it up where it's like 4 credits of lecture content. So it's like more on us, but it's really 2 credits of homework. That math doesn't make sense, but if you get my and at the beginning of every class, we're just going to have a really brief quiz just to kind of double check if you're kind of paying attention and kind of following along, just so that we know that the things that we're teaching are actually sticking, and kind of if we need to revisit any topics as we go along. And finally, one of the biggest things that we're hoping for you guys to have as an outcome of this class is to kind of have this final toolkit, is to have this kind of reference resource where you are able to use it later in your career, later at Olin, and just have something that you can actually tangibly leave college and feel like I could take on a Mechie problem and actually like just see all the resources right in front of me and go for it. So yeah, we're going to be introducing that more, and there'll be check-ins for this final project. And you can see kind of the gist of it and like the intro blurb on the Canvas. For how this course is going to be graded, if you've taken thermodynamics before, it'll be very similar, but we're using something called specifications grading, which basically means we just kind of have almost like a contract. These are basically the minimum requirements of just completion that you need to do in order to get these different grade bundles. So as long as you get a definition of complete, which is in the syllabus, but is basically just turning something on time, doesn't mean like it's completely right, but at least you kind of attempted at the problems. And then you're allowed to like iterate and kind of resubmit until you get an actual complete, as opposed to just staying as an incomplete. And basically you kind of know from the get-go what it takes to get a grade in this class. But we're hoping again that this is kind of more formality, and really a lot of the learning is going to happen through the lectures. So I'm going to do a brief run through the Canvas.
Real quick.
So the majority of the information that's relevant is going to be in the syllabus. So you'll find kind of like citations for the textbook. This is where we're going to post office hours. And then we're also going to put all the office hour announcements in Canvas, and also just Discord, just for the sake of allowing people who maybe want out of this course to actually be able to kind of get in on the information that's coming up. And then, like I said, here's the grading policies and kind of the definition of complete for this specification grading scheme. And I think the last thing, just to remind you, you might not need it for this course, but just in case, there are tons of resources that Olin provides for academic support. So just please be aware that those are options for you to have throughout the semester in your Olin career. And last thing, so everything on the Canvas is posted from the beginning. So you're going to see kind of the gist of what we're working for. There are a couple lectures missing from the end for our final project time, but this is all the lecture topics. You kind of have a sense of what we're working up towards. Before every lecture, we're going to post the lecture slides like on the day assignment. So you can always download it ahead of time or follow through the actual lecture itself. And then afterwards, we're hoping to put like recordings and stuff like that, just so that in the end, we can share out this information and help folks, beyond the scope of this course. And I'm trying to think if there's anything else. Yeah, and then any resources or any of like these textbooks that we've been referencing, we're going to put on files, and we'll let you know when we finally get that up to date. So just
is already up there.
and then for our first homework, so because these first 2 weeks are kind of weird, it's not due until the 12th, which basically means that they're going to be due at kind of the Monday morning before every single week. So every week's kind of lectures are going to feed into that homework, and then you just basically need to submit before Monday. Any questions about the Canvas? I think it hopefully should be straightforward. Right. How do I switch? Okay. So like I was saying, yeah, office hours are currently kind of working up as people find out their schedules. I will have just like an hour of office hours tomorrow in the library from 1 to 2 if you want to talk through the course and learn more. But I wouldn't expect a ton of things to come up yet. But again, they'll be there if you need them. So you saw that we've been kind of using Notion, we've been mentioning Notion, and we just kind of want to introduce why that's even a thing in this course. So the hope for a lot of the learnings that we're going to have and what we want to hand off to the ME faculty is ultimately to improve the ME curriculum. So through that, we want to kind of share these resources, share any of the course content. So we're using Notion for kind of our internal purposes, just so that we can eventually put this all on like the Olin GitHub and actually have this as a public resource. And then Notion also allows more collaboration and nice formatting. So we're going to put all like the equation sheets and some of the aspects of the course on there for you just to have as like a kind of like online web resource as well that you can reference. So just so you can see those profiles. Oh, wait.
Use the app, not the thing.
Should have pulled this up ahead of time.
So probably towards the end of the class, we're going to get a lot more like ask you guys for feedback and surveys, and that's going to go up on the Notion, anonymous, all that jazz.
But yeah, if you guys have any ideas about like how we could eventually share and actually make this something that lives beyond just our own careers, we'd love to hear it. We really want to try to see kind of like more like long-term documentation for like ME resources, because it seems like, it's not worth everyone kind of redoing the same groundwork when we can all kind of collaborate and make something that's better than the sum of its parts.
Just
It's okay. He's gone. Okay. I won't mess with it. The Notion is acting funny right now, but it's not a huge deal. There's not much that's really relevant to the course at the moment. But like you saw for the content review stuff, we'll probably put out more stuff on there so that you can actually reference it long term. And like I was mentioning before, please just get on the Canvas and the Discord for any announcements. We're going to be using Discord sometimes just for like kind of announcing lecture topics, because there are a handful of people that do want to audit the course or just sit in on random lecture topics. So if anyone's auditing the course, just know that we're going to announce stuff there.
That's also probably the best place for you to ask your general questions and stuff, like
Things that'll help the whole class.
yeah.
Like, also feel free to reach out to any of us individually if you like are struggling or need help or just have a question that it does not pertain to everybody.
Hello, we also have CAs for the course. You guys want to take a quick second Introduce yourself, sorry. Not to put the onus on you, like,
Hello, I'm Liv.
Nice. Name, pronouns, and then what's your preferred way to communicate? Like if someone has a question or something.
I use they them, I'm fine with anything, probably easiest would be Discord or text.
I'm Anisha, she, they. Anything works. Discord is probably the easiest. I think I'm doing it on there.
We should talk.
I'm Laurel, she, her. I kind of will use most platforms, Messenger, Telegram, Discord, but Discord's usually the first one I quit. Please don't Slack DM me. That one also gets quit when I don't want to think about working. Email, I guess, but that feels very small.
Bennett is also a class CA, and so we'll get him up to pace too, if you ever have questions. But thank you, CAs. Woo! They get paid, we don't.
We're paying, actually.
Yeah. Don't scope me.
All right. So a little more detail about the final project real quick. Again, we'll cover a lot more about this later on the semester. But just kind of get your head around this. As Colin was saying, there's kind of two main parts. The first part is building a personal reference resources, we're calling it. So basically the idea is over the course of this whole semester, you compile all the stuff from like all the equations, all that kind of thing, compile it in like some context also, compile it into one big thing. And so that make it easy for you to reference later in the future. The second part is a individual or pair research topic. So you can choose, do it by yourself or do it with a friend. You like basically find a type of analysis that we didn't cover, research it, figure out how it works, stuff like that, and then add it to your reference resource and then share it with the class. We're still trying to figure out the final form we want to do, whether it's like mini lectures or some kind of gallery walk. We're discussing that internally, but yeah, basically find a new topic that we didn't cover, research it, and share it. A couple examples of a reference resource from our wonderful Colin here. So some of you may have seen the review sheet before, but basically anything goes. We don't care how you set up your reference resource. You can do it on paper, like if you have an iPad or something like that, you can do it on OneNote, whatever noting app you want. You can make a giant Google Doc full of everything. Notion's also awesome. Colin's Notion is spectacular. It's awesome. So whatever works for you works for us. That's totally fine. We just want to help you build something that's accessible for you in the future. Also, it'd be cool if you set it up so that you can add other courses to it too in the future. So all of your notes are organized like that. That's up to you. But you can use it like that if you wish. Yeah. So in the first or second homework, we'll probably have you guys kind of do some research about different types of organizations and things like that, and kind of help you lock in on one so you can start adding the stuff we talk about as we go, especially as we kind of exit the review phase and start into the more stuff that's new material. At that point, we'll want you to ideally add to your reference resource over time. Some course expectations. This is a new course that we're adapting and adding stuff to and taking stuff away from. So please excuse the bumpiness as we kind of iron it out. Please speak out if the tempo is not right. Just talk to one of us. We'll have a feedback form we'll get to in a second. Just basically communicate if something doesn't make sense, if something's not right. We can, this is an experiment, so we can, throttle up or throttle down as we need to, as what works for you all. And yeah, it's an experiment. Experiment with us, give us feedback. We want this to almost be like a co-design, right? So we want feedback from you about what we're missing, what stuff that we've already covered or you've already seen before, and we can skip stuff like that. So yeah, please help do it with us. That said, we have a semester feedback and kind of questions form. This can be anonymous, or you can put your name on it. It's up to you. There's options in the form. So this will be linked a couple different places, linked on the Canvas. It's linked here in this presentation, so you can always find it. So it'll be a semester long thing. If you have any anonymous feedback you want to share, add it there. Or if you have a specific question that's not right for Discord or not, something you want to ask privately, but to all of us, you're welcome to put that there as well.
Additional resources or anything, just so you guys know, when you do a student-led course, you have two advisors. You have your content advisor and your pedagogical advisor. Daniela Fuss is our content advisor, and then Rob Martello is our pedagogical advisor. So like we won't use your name if you don't want us to, but if there's ever anything actionable or something that like really is insightful for us that we want to pass down, it might be shared with us individuals. But yeah.
All right,
We do like a 5-minute bio break.
that works. Yeah.
Yeah, quick 5-minute bio break, and then we're gonna just go through some materials. And then we might get out of here just a little bit early. See. Yay! 40 minutes, right? Nice.
Would it be possible to get linked to the Kansas site?
Yeah, I could try. I don't know,
Okay.
honestly. I think we should be able to add you. Or Daniela can for sure.
Okay.
Yeah, I guess it doesn't matter. The registrar doesn't care.
Yeah.
Yeah, he's been doing that. I'd be. I think so. If it's a problem, then let me take it. Oh, yes, we go.
You got some serious Zoom center.
Yeah, I know, right? Colin really pulled all the stops there. Yeah, it's good. It's so fancy. It looks good on the Zoom. It's really good. Yeah. Yeah. Oh my gosh, come on. Yes, thank you for coming. You are free to go if you would like. Yes. Also, thank you guys for being CAs. It's awesome. Really, really super appreciate it. Zeno, you should be added
Oh, thanks. Awesome. See you on the next. Tuesday.
next Thursday. Because Monday is a holiday. Does everybody else have access to the canvas and everything? No other issues? Okay, no. Mute.
Yeah. I'm gonna say, I've heard, yeah, I'm going to try out. It's like, I've always done the internship, I feel like I never.
Yeah.
Oh, that's a good one.
Like, that's why it's almost like the whole like, oh yeah, this explains that to right now.
Yeah. The public hearing, you would go for the-
Like,
yeah.
like you're up in that.
That's a take. Not that it's wrong, but interesting. That's an interesting thought, though.
What is?
Like survival biaship towards like when you take notes like by hand versus type it up. Like
No,
if you take notes by hand, you don't like always go back and reference them.
Mm.
I do that quite a bit.
Pedagogical like research says like handwriting.
Yeah.
Oh, yeah,
handwriting's definitely-
handwriting and like physical handwriting versus like iPad apparently is still better. Versus
Oh,
typing,
really?
yeah.
Wait, so like
It's-
pen and paper versus like
Yeah, it's just like
notes?
distraction factors, I think.
Okay. When I got my tablet, like just the lack of weight and like carrying around 6 notebooks just felt so much better for me.
Also really cool.
That's and that
And then one
And
that
then
is, yeah.
exactly. And yeah, I had a so sorry, not to interrupt. Yeah. I had that Rocket notebook and that was helpful for a while, but then like it's just a lot of maintenance for it too. Where like of constantly having to wipe
Yeah,
or go
maintenance is
through.
not.
Yeah.
Didn't work though, did the rock and thing work pretty well?
I liked it a
Yeah.
lot.
I wasn't curious about that. But
I liked it a lot. And they have stuff for like you can do it for whiteboards now too, which I think like like, because the smart boards never worked, and then just pictures of that was always good, and it has OCR as well, so I always really enjoyed that. All right, William Lazzino, everyone else is back. Yep, cool. So we're gonna do two quick things. We're gonna really basically, at a very basic level, describe free body diagrams and go through just a sample example of one. And then we're gonna go into some like mechanics of materials stuff. Please raise your hand if something's not making sense or you need something clarified. I mentioned before, Daniela is our content advisor. And so we're going to do like a quick blip of like her take on why all of this stuff matters and how it like kind of all concedes and go in together. Free body diagrams and kind of basic fundamentals materials is really your fundamentals for solving mechanical problems. Like our assumptions when we work with Newtonian physics, if you have a rigid non-moving case, it works pretty well and it's pretty accurate. And this is the first step into getting into how things break and why. So free body diagrams, this is going to be a big wall of text, but we'll walk through it. When you start, you want to define your system. So that means like, what are you actually analyzing? What are the limits of it? And what is your boundary? Represent that object as either like an actual body or a particle, and then completely isolate it from all supports. So that means like, that is what the free and free body diagram means. Like if it's sitting on something, remove that. If it's hanging from something, remove that. Whatever it's touching, the way I think about it is whatever it's touching or whatever is touching it, get rid of it. And then what you want to do is that instead of drawing whatever's touching it or whatever's acting upon it, represent that as a force. And the key thing with this, and what a lot of people mess up when they start doing free body diagrams, is that anything inside the boundary, like inside that barrier you've drawn, you don't want to draw forces acting inside that. There are no internal forces. So we'll do a quick example of that. You want to make sure you have, and by the way, you want to have a chosen consistent reference frame, always draw it out so you have an idea what you're talking about, especially when you start getting into stress transformations and things. And then if there are multiple bodies within your system, you want to draw a free body diagram for each one of those individually and double check yourself. So remember Newton's third law, equal and opposite reaction. Like you make sure that your forces add up and you're not missing anything. So as a real quick basic sample, we have very simple, like 2 blocks on a plane. One of them is a bigger mass, one of them is a smaller mass. There's a tension that's applied to the bigger mass. On that plane, there is no friction between the bottom block and the plane, but there is friction between the top plane or the top block and the bottom block. I want you guys to either in your head or actually sketch it out, make a free body diagram for just the small block, like just the top block. All right, feeling kind of good about it. And this is not quizzed or anything like that, so don't worry about it.
This actually determines your final grade.
Yes, entirely. Free body diagram excludes the shitty just hand-drawn stuff. Does it look something like this? Sound good? Does someone want to explain to me why friction is pointed in the direction that it is? Any brave soul?
Always opposes motion.
Yes, sir. That's a really good way to think about it. It's kind of also like a damper. I like to think, like, keep those two in my mind. It's always going to oppose the way the object wants to move. So that's a very good way to like think about it. Okay. Now let's go for the large block. Same concept, just the large block.
You did a Jeopardy song, but
Anyone need more time? Doing good? All right. If your diagram looks something like this, you're doing on a great track. The important things to point out here is that both your friction and your normal force that we're acting from block one are going to be equal and opposite from how it was before. And that's where kind of people get a little confused on a lot of things, that if you have two objects that are in contact with each other, the force needs to be equal and acting in the opposite direction. So the friction that is acting on block one, because it's holding the smaller mass, because it's holding up in the first free body diagram, and the second one, it's going to be acting down or acting downwards. Similar, same thing with the normal force. It's like very tempting to be like, oh, gravity is just acting straight downwards on it. That's not the force that's acting upon it. There is a normal force that is equal and opposite in the other direction. And like, you can also kind of do the think about it that way of like, if you add head to tail, both the normal force and the friction force, it should look more like that gravity acting downwards. So you can kind of break it into components. But I like to very specifically point out these should be equal and opposite. And then of course, there's no friction on the bottom slide. Rajiv, did that answer your question?
Still confused why.
This bottom side's frictionless.
Oh, okay.
Yeah. Mhm. Okay, last activity. Make the free body diagram, but now your system is both blocks. So there's two bodies in this system. Oh, she is? Oh, nobody let us forget. Katie wants a selfie with the entire class before she leaves. So make sure that happens before we get out. Oh, we can take it on camera. Yeah. Feeling good? Cool. So this is what your diagram should sort of look like. You have two bodies within your system, so you want to draw them individually. Your body forces are acting basically the same as they were before, except now friction is an internal force to this system, acting between those two components. So you don't want to highlight those. Same thing with the normal forces between the M1 and M2. When you are analyzing individual components within your system, that's when you need to include the body forces acting on the individual body. But for free body diagrams, the important thing is, what is your system? Be explicit about it and make sure you're not drawing internal forces acting upon it. So like, for example, if I have a wrench tightening a nut or something like that, if my system is the entire wrench and nut, I don't want to draw the normal forces acting between the nut and the things. If I'm drawing just the wrench and I'm analyzing just the wrench, I want to figure out what the shear force is acting upon that. That's when I do need to include those. But like the hardest thing that people get tripped up with internal free body diagrams, at least in my experience, is figuring out when to include those internal forces and how it interacts with other systems. So two important things: make sure all forces are equal and opposite to each other, and also make sure that like your system is well defined and you're not adding extra forces that don't need to be there, should not be there. The other thing with free body diagrams and the way we're going to be looking at joints and stuff like that is that you need to be able to analyze different types of joints and what sort of reaction forces they impose. Reaction forces and reaction moments. On the left side of the screen, you have your most common joints that you're going to see like written out on free body diagrams. A roller joint is usually drawn as like three balls together. That only provides a normal force. So that means it's not constraining in the X direction or whatever your system is. It only provides one normal force on the way it's acting. Your pin joint is kind of like similar to a door hinge or any other examples, that provides a X and a Y component normal to each other, but it doesn't provide any moment. So like the door hinge, I can't rip it from the wall or anything like that, but it doesn't resist a moment, so it swings around. And a fixed is usually a pin joint, by the way, is usually drawn by a triangle right here. There's usually sometimes a circle in the apex of the triangle to represent there's like a pin going through that it can swing about. The last thing is a fixed joint. Fixed joints are welded, bonded, bolted down. They provide both two normal forces and a moment so that you cannot it is permanently fixed there. We are acting as if it is a permanently stiff, nothing can move it from its position. Do fixed joints exist in actuality? No, but this approximation is really close and helps us with analytical tools, what we want to get to. On the right, we have some more diagrams as you might see them in written out in the world. In your homework, you're going to be asked about bearings as well. So journal bearings don't prevent rotation. It's kind of like a pin joint where you can slide, but it doesn't stop any axial load. Thrust bearings prevent axial loads. And so that's a question that's going to come up in your homework. You should make a written note of that, or if you have any questions, reach out to any of us. I also want to take the time to kind of point out some, can you go over here? Sorry about that.
No worries at all.
I wanted to point out some real world examples of what these pin joints actually look like or what these joints actually look like in real life. So these are in the lecture slides. And if you scroll down, I like this website because it has a free body paper representation and actual photos to represent, okay, this is what a normal reaction looks like. This is a 2-force member. It can act in tension or compression, but it doesn't prevent any moments. Here's a frictionless pin. Here's a sliding collar where it will prevent it in the Y direction and will stop a moment, but it doesn't allow it to slide. And here's a fixed joint where it's actually welded. They also have 3D reactions when you start getting into more than just XY plane. And just seeing these in real life, and I kind of like doing this just in homework or in the real world of looking around, how would I represent that in a free body diagram? How is this fixed? How many degrees of freedom are removed? Yeah. Oops. Is this it? No. He knows what he's doing. I don't. Cool. Oh, there we go. That's my biz.
So I'm gonna probably do this on the Blackboard in a second, but I just want to touch on, so I'll explain this more in a second as we go through kind of stress strain curves in 1D. But there's a point on this slide that I think is just interesting as just a side, is we were talking about, we want to give some practical engineering knowledge. So the idea that my modulus of elasticity or my Young's modulus doesn't change when I have heat treatment or alloying. This is actually a really common interview question. I've gotten this on a bunch of different ME technical interviews, and this will look like this on an actual stress strain curve. So this is just a random research paper that I found that just very clearly shows that even given any heat treatment, that my actual kind of elastic region or this kind of linear region doesn't change, but everything after that fact can change. So you'll see this in questions one that I've gone before is that I have 3 different springs of, one is made of mild steel, one is made of case hardened steel, and one is made of aluminum. Please order these springs in ascending order of your spring constants. And basically they're trying to test if you know this, and it's going to be a trick question. My steels, regardless of the actual heat treatment, is going to be the same kind of modulus of elasticity. So I'm going to have the same spring constant, same geometry. So it'll be, my steel is always going to be stiffer than my aluminum. And basically they're testing your stress strain knowledge. But yeah, that's just a quick aside. That's a common question you'll get on some very kind of first round ME technical interviews. But I'm going to.
And again, these slides are on the website if you would like them in written form, but I highly recommend. Oops.
I'm going to do Chris really quickly and brush through all of your mechanics and materials. So just to remind you, I'm going to talk about load displacement relations. So I have my load to my stress. my screen. Finally, to my. Question. We'll call this. And then an in-between step, kind of at my stress, I also have failure or fracture. And also I'll put these notes on the canvas after the fact, so you don't feel like you have to write any of this down. And you probably have it if you're already done mixed solids. And this is just breaking and whatever your definition of failure usually, like it might be stress or ultimate tensile stress. So 1 to 2 is by geometry. And then I think 2 to 3, there's like something that's not touched on in mixed solids, is like this is actually called a constitutive or like material law. I didn't know this at the time, but I just think it's interesting that these are kind of like man-made kind of quantities of materials, and that these aren't necessarily measurable to the extent of like you wouldn't find strain directly, but you're kind of making these man-made jumps for useful intermediate quantities. You don't really need to know that, but I just think it's interesting. And again, we're just covering kind of like 1D stress. That just means my Young's modulus is equal to stress over strain. And then 3D, a far more complicated. I won't touch on it right now. But as a reminder of our stress strain curve for engineering stress strain, I have my elastic region. Give me a second just to draw this. So I have my elastic region, and I have my proportional limit, point A. I have point B, which is my yield stress. So on an idealized stress strain curve, most of the time, they're just saying, I'm going to take the slope of this line. For things that are more kind of concretely in like reality, like when you do aluminum, for example, for a stress strain curve, this is less obvious in kind of its linearity. So you'll see like the 0.2% offset method. And that's basically just taking like an offset of 0.2% of my strain and just making a parallel line to that. And that's just, again, because real life data is really hairy and complicated and maybe not as obvious as these idealized curves. Like if you remember the Mech Solids tension lab, that definitely is very true.
Also, we're saying like this is a linear model for non-linear behavior, but it works pretty well.
Stage effect.
Yeah. Just ask the crowd, and please, does anyone need a refresher on what stress and strain is? Okay. So while Colin writes this, stress, and if you go to like slide here, yeah. If you go to slide 44 and 47 in your lecture notes, there is kind of like actual formulaic definitions of it and a kind of like written definition of it. Stress, the way I like to think about it is that when I apply a load to a body, unless that body's going to fly away or something like that, there needs to be internal forces and internal like components that keep it in place. And when you apply stress, there's a defined strain associated with it where it's going to stretch past its original position. When you're in the elastic region, it bounces back after you remove the load. When you go past that, it's going to be permanently deformed and not going to go through that.
Yeah, so on that, remember I have my elastic region, and then I have my plastic region, and then they're kind of subdivisions of those regions. So you'll see this kind of like plateau section, sometimes called like the perfectly elastic region. It depends on kind of the material, but you'll see this in some stress strain curves. And then I have my strain curving section. So this is kind of when I'm actually getting to the point where I'm putting actual permanent strain into my material. So the idea, if you've ever messed around with a paper clip and you just put it back and forth, you kind of see strain hardening or kind of the buildup of that strain. And then after I get past my ultimate tensile strength, which is point D, I get into this necking territory. So again, that's just, for dog bone as I'm actually pulling the material, it's just kind of pulling in and my area is actually changing. So that's why, again, this is only representative of a engineering stress strain curve, because this is kind of representing a downward decline, which isn't close to reality when my area is changing. So from my actual real stress strain curve, you remember that my fracture point would be up here if I actually took into account that my area is changing as I'm actually pulling my material. And these are really good assumptions for 1D elastic cases, but these are not necessarily representative of brittle materials. So brittle kind of failure theories are something that isn't really touched on at Olin. It's more common, like a lot of civil engineering concepts. We're going to touch on them more in later lectures on like static failure theories, but just know that I, of course, don't really have an elastic region. I more just have my plastic region into kind of instant fracture when it comes to brittle materials. And there are also a lot of different ways that I can analyze and kind of predict that failure as opposed to VCs, which is very common for ductility. And I guess the biggest thing, just as a reminder,
What is the difference between a brittle material and a ductile material?
That's a great.
And what are some examples?
So like,
Good plan.
the easiest way to think about it, most of the time for most materials that are ductile or brittle, is that for my ductile materials, it's about the same for tensile strength and my compressive strength. That's like the equivalent way of thinking about it. And then when I think about my brittle materials, I like to think of it as just most of the time my compressive strength is going to be far greater than my tensile strength. So you can think about like on the highway when you have those big concrete pillars. I'm always loading those in compression. I'm never going to see like a suspension bridge made with like pillars pulled in tension. And that's just like a good rule of thumb. That's not necessarily, there's probably edge cases that I'm not thinking of currently. And I'll go into kind of the ways that we actually think about the failure theories that take this into account. But that's for the majority, I guess, from a strength perspective, how to define it. You could also think from like a math side perspective of like ductility and the ability to actually pull it. Oh, I'm sorry. Yes.
What is what?
That does not count as a complete in your homework.
That is true. I wrote it.
Stress on your y-axis and strain on your.
What are the units of stress?
Units of stress and strain. So my strain is going to be unitless. And that's because it's a length over length kind of quantity. Now my stress, most of the time, you're going to see in like pascals, more commonly probably in megapascals. Or sometimes I guess gigapascals. It just really depends on the material. So I guess like some common materials that you can think about, like 6051 has a Young's modulus, 9 Pascals, has a yield strength of 72 megapascal. So there's just a general order of magnitude, and compared to like 4130, let's say it's like the ultimate tensile strength is like a little under double of like 6061. And these are commonly found, you'll see like we had mentioned it before, like MatWeb. It's a common example of finding example material properties. You just know that those are kind of hairy when it comes to actually using them in a lot of analyses. It even says actually on that website, these are not meant for like kind of analysis purposes. I mean, that's mostly because materials really are on the basis of kind of my actual vendor, my actual kind of performance when it comes to, I guess, like where it's being manufactured and heat treating. So it's really good for educational purposes to use those in your analyses. But just know when you go into industry, you're most time going to be working with your vendor, getting actual mat side properties from them. And there's going to be far more a greater breadth when it comes to the variety, I guess, sorry, not the variety, the variability in your material. I'm going to try to touch on it later in the course about the ideas of using like better stats methods when it comes to looking at material properties. Like ZDR really talks about this a lot in his courses. But yeah, like factor of safety and some aspects like that are not very descriptive when it comes to thinking of things larger than kind of a volume of one. When you actually make, you know, hundreds of thousands of parts, and how do you predict failure? That was really fast. Oh, sorry, good.
Can you, sorry, if you're done with that point, can you explain a little more about the region?
So this is just as I like plateau and I have kind of, I'm taking on more strain, but I'm not actually having any induced stress. And I can't remember exact like material like curves off the top of my head, but this is common. And I think like more aluminums that you'll find like a perfectly elastic region. So it's, yeah, it's just literally it's plateauing and I have no change or no slope, I guess, in my stress for a small period of time.
Okay, but it's still returning to the same.
Yeah, so this is still like point C is still my elastic region. So if I was kind of following my curve, it's still come down. But like past that, then I'm kind of setting permanent strain and would have like a new stress strain curve that comes down that is parallel to my elastic, not my elastic, my Young's module.
Yeah, it's not a point we made slides on, but it is worth noting that when you are still in that elastic region, when you unload it, it's going to come down at the same slope of your Young's modulus. And then, like Colin said, there's an entirely stress strain curve that is now like permanently deformed from that point, sort of, but it's unloading.
You pass the elastic. So
Wait.
up until point C, you lower it still follow that. That's how
There's probably, this is like a very idealized case, so I don't think it's.
Generally, the ones I've seen for aluminum, it's like linear mostly, and then there's kind of like a round over point. It's kind of like a big fillet, and then it kind of shoots off in this big like parabolic arc. Different materials look different, but
So for the most part, yeah. But like, I guess I don't know about to be perfectly frank, the perfectly elastic region. But when you're in your elastic region, the rule of thumb, yeah, is I'm following kind of that linear curve.
also it's where failure is defined is also different, like you mentioned earlier with that rule. The
Point of two.
Yeah. So failure definition is not always like. I mean, like in this case, if you're going all the way into that perfect deformation or the perfect elastic region, failure could be defined as before that, depending on. So yeah, just keep that in mind.
Yeah, because these are all approximately, realistically, these are actually averages. Since I'm just an engineering curve. So yeah, they're kind of hairy when you think about like real world, like kind of ethical applications when it comes to safety, because the average is very nondescript statistic when it comes to failure with like really low margins of safety, like, you know, in aerospace, I have a factor of safety of like 1.2 or something like that. Or actually, you can't even use that. You can use like a percent failure as like the way of managing actual risk. So yeah, I'm hoping to touch on this more in the course. It's something that's really not discussed. But are there any questions about this?
I've heard about like plastic regions. Where does that fall?
So plastic region is everything past kind of point C, so like all the way here. So plastic region is being defined as like when I'm actually putting in permanent set or like permanent strain. And what I was mentioning before, when I actually am unloading and reloading my material, it kind of returns to a different spot. So it's almost like, to use the paperclip example again, it's like, you know, I bend it a little bit and it'll return to place, but if I bend it too far, it'll kind of set and that it'll like stay back basically. So it's anytime that I'm actually kind of permanently deforming my material.
So even if like the 4 point C in that flat region will go back to 0 straight.
And yeah, in an idealized case, for most materials in my elastic region is just going to return back to its original form or original length. But this is again like a 1D stress strain curve, so there's a lot of nuance when it comes to actual examples. Oh wait, there's one more thing I want to touch on. Is the idea of a couple other statistics you'll see talked about. So you'll see my modulus of resistance and modulus of toughness. And these are ways to think of it from maybe more of an energy perspective of like how much energy can I put into my material before it fails. So underneath my elastic region, I have my modulus of resilience.
Yep. Resilience.
I think colloquially, it's easier to think of this as like how much energy can I absorb and like not actually deform, and like how much can I almost like put into it that it can take that doesn't actually put any permanent set into it. So you'll see that more when it comes to applications for like crash testing or something like that. Like what is the amount of energy that I'm putting into this before this breaks? And then my modulus of toughness is this entire region underneath the curve. And then the same kind of colloquial definition. This is kind of more the total energy that can be absorbed for total failure. So this is like basically thinking about like how much energy am I putting into this one material before. Yeah, I guess you'll probably see these more in like dynamics and kind of crash testing and things that have like a really quick kind of impulse when it comes to an energy perspective. So maybe less so in kind of your statics policies if you actually use that, but there are a lot of things outside of all limits. Do you want to talk about this example? Because I don't know what
I have to.
Yeah.
The brittle and ductile stuff, or
Yeah.
the cool. Just to reiterate on what Colin just said, and you will need this slide for your homework. Like resilience, exactly as Colin said, it's the area of like elastic, it's the area underneath the stress strain curve where it's material still acting elastic. Toughness is the entire area. There is no deformed like way to do this besides like doing actual calculus for an actual sample of stress for a tension test, but we do have a good approximation for how you can get a very good like approximation of that value. So this is on your class notes. Right here, we're going to go through some examples on like how to actually like start telling the difference between brittle and ductile failure and just kind of like what the difference is, how it visually looks. So based on what y'all know about ductile versus brittle materials, these are before and after photos where you have a 1D test case where it's just loaded in tension. Which one of these do you think is the ductile? Which one of these do you think is the brittle? Shout it out. Nice. You want to explain your reasoning why? Exactly. All right, so that's a 1D tension test. How about something more like a compression test? Yes, sir. Same thing where you see actual permanent deformation there, and more of a shearing that you'll see in the brittle or a 45-degree angle pace. How about a bending test? Yeah, I did intentionally switch them. So you guys didn't answer left every single time. This one's gonna be a little more difficult, and I don't have an perfect explanation why. But let's talk about torsion now. Yeah. I need to do a little more research on the exact reason for that, because I don't have a good explanation for that, but a good way to think, and like we can also supposedly, Emily tried to do this in Next Solids, and I haven't even tried to do it, so hopefully this will work. But ideally, take a piece of chalk,
pretty brittle material. A little like twisted, you get a 45 degree.
I have no idea. I think Carlos just pulled it from the
Is that
end.
from like the whatever inch-strong,
What's that? Like twist tester.
The curve.
the markings on the test piece?
That's what I was thinking, yeah, where it's like, I doubt it has been twisted that many times around. When I saw these samples, and I think this is just like a aftermath of like the actual test environment. Because there's no way you're getting that much like change in your rotation for fractures.
It's also very consistent across the length.
Yeah,
Just suspicious.
yeah. What's up for you?
Could it be related to like minimizing and maximizing like the cross-sectional area type E? Like, could that be part of it?
Part of the 45 degree thing.
Yeah, like why it like.
Oh.
changes the, like,
We'll circle back to that in a couple of
Okay.
weeks.
Yes, so there's some actual math about, yeah, there we go. But I mean, if you guys want to grab a piece of chalk around here and twist it, it should.
Does it work?
45 degrees, which is actually pretty neat.
Science.
Don't break all Chris Lee's chalk. though. What's up? My finger.
You're welcome to test out yourself.
You are more than welcome to give it a quick, yeah. Avery, one more thing. As Colin said, we'll touch more on this material, like how different materials fail. So we'll talk about stress transformations and get into discussion around Moore Circle. We won't go super in depth on Moore Circle. We're just revisiting because I think it's a very good way to like get into failure theories. Because a lot of old failure theories before you had FDA was dependent on like mapping it out and seeing what region you're existing in for like local hormesis, stress, and a bunch of other failure analytical tools. But do y'all three have anything else to say?
Yeah, just a couple quick reminders. So, we are kind of speeding through some review for today and then next week. So since this course is kind of a bunch of different variety of backgrounds when it comes to previous knowledge, please kind of rely on like just asking us questions, or if you want more practice problems or example chapters, we're happy to provide them if you need more review. Again, I'll be in the library tomorrow from like 1 to 2, and I'll probably be there longer if you want to be able just to talk through things more one-on-one. And hopefully we'll have office hours set up in the next week so that you can actually start utilizing those as we kind of clear the cobwebs of this past summer. And then the last thing is please just double check the Canvas for me, make sure that everything access-wise is working and that you can see all the homeworks and the assignments. If that doesn't work, please just send me a note. I think that's all I could think of.
Cool. Well, thank you guys for day one. Before anyone allowed to leave, we take a group photo.
Do you need a big camera to just do this?
Huh? You just need someone's phone. You want to use your phone? You just send it.
Should we go back to the slide? Take it back there, or take it.
I'll go to this, yeah, first slide. We got it.